f of x is going to be the natural log of 1 plus x. And we're going to try to find the arc length of this function's graph from 0 to 2. The graph of ln of x looks like this. It doesn't even exist at x equals 0. And in fact has a vertical asymptote there as x goes to 0 from the right. The function we're trying to find the arc length of, though, is ln of x plus 1 instead of ln of x. This is y equals ln of x. Replace x with x plus 1. That's going to translate it to the left by 1 unit. This is going to be the graph of y equals ln of x plus 1. And we are after the length as x goes from 0 to 2. The length of this piece right here. This is something I'm about to show you that you should be able to do on the exam. You should be able to estimate that length using the length of a secant line, if I asked you to. Where does that length come from? The Pythagorean theorem. There's a right triangle in here. We could use the distance formula or the Pythagorean theorem to figure out the length of that line segment to be square root of 2 squared plus, if you plug in x equals 2 right there, you get ln of 3. ln of 3 squared. Use technology. ln of 3 is a bit bigger than 1. I've got to square that. Add 4 to it, and then take the square root. About 2.28 is the length of that blue line. What about the length of the red curve? It's going to be a little bit longer. I guessed in the first section, I guessed 2.4. Okay. Turns out to be really close to 2.3, just barely longer than 2.28. It's about 2.30. Let's start the calculation of the arc length. And I do want to show you, you can get to a point where you can do the integral, but it's tricky. This will be good practice, though, with theoretical substitution. I need to integrate square root of 1 plus f prime of x squared, so I have to find f prime of x as well. That's going to be 1 over 1 plus x times 1 because of the chain rule, which is just 1 over 1 plus x. That's the derivative. I have to square that, add 1 to it, take a square root, and that's the function that I integrate. Yikes. Doesn't look like it's possible, but amazingly it actually is, though it's not easy. I'm going to, well, okay. I can write 1 as 1 plus x squared over 1 plus x squared. And then I can add 1 squared to the numerator. To get the square root of, I'll write it as x plus 1 squared plus 1. And in the bottom, I've got square root of x of 1 plus x squared. Effectively, the square root and the square root cancel, leaving you with just an x plus 1. Technically, it's the absolute value of x plus 1, but x plus 1 is positive here. It's a definite integral. We really should check that. It's because x is between 0 and 2. So that x plus 1 is between 1 and 3. Definitely positive. X plus 1 is positive for x between 0 and 2. All right. I did decide to do a substitution right away here. You maybe could do this with one substitution, but I did a substitution that I was unsure was going to be helpful. I'm going to go ahead and redo that substitution. I'm going to let W be this entire thing in here. W is going to be x plus 1 quantity squared plus 1 You can expand this out. It does equal x squared plus 2x plus 2 in the end, though it's not really necessary to expand it out. If I find dw, it equals 2 times x plus 1 dx. By differentiating that, I did it with the chain rule, actually. And I can rewrite dx ultimately in terms of dw by dividing both sides by 2 times x plus 1. I can write dx as 1 over 2 times x plus 1 dw. However, for that to be helpful, I need to replace x plus 1 with something involving w. Well, that can be done. Going back up to this equation. Solve for x plus 1. Subtract 1 from both sides, then take the square root. X plus 1 is going to be the square root of w minus 1. Okay, again, it's not clear that this is going to be helpful. You're just sort of blindly trying something and seeing what happens. I can now use this to rewrite this in terms of w. 1 over 2 square root of w minus 1 dw. X plus 1 is positive for the definite integral, so I can take the positive square root here. Anyway, after all these replacements, what's going to happen? In the top, I get the square root of w. And the bottom, x plus 1 gets replaced by square root of w minus 1. But don't forget the dx has got to get replaced with 1 over 2 square root of w minus 1 dw. And if I want these to truly be equal, I do need to change the limits of integration, which you should know for the exam. How? Use this equation. When x is 0 in the original integral, plug in x equals 0 there, you'll get w is 2. The lower limit's going to change from 0 to 2. You've got to make the change if you want these things to be equal. When x is 2, this equation gives 2 plus 1 is 3 squared is 9 plus 1 is 10. The upper limit becomes 10. Now this integral doesn't look any easier to do, though it can be simplified a little bit. I'll factor the 1/2 out in front. Doesn't really look any easier to do, but it actually is a little bit easier, I think. I'm going to do yet another substitution. Sometimes you got to do more than one substitution, just like you have to do integration by parts more than once. I'd like to try to convert this to a rational function that doesn't involve any square roots. That's my thinking here. I'd like to convert that to a rational function that does not involve any square roots. How? Try letting u equal square root of w. Another new variable, u. Then the square root of w in the top will go away. I'll just get a u. And in the bottom, w minus 1, that's going to involve u squared. If u is square root of w, then u squared is w. And w minus 1 is going to be u squared minus 1. I do have to find du. I haven't done that yet. Du is going to be, differentiate this, 1/2 w to the negative 1/2 dw. So dw is 2 square root of w du. Get that in terms of u, it's 2u du. Wow. I believe this is right. I believe I have not made a mistake. Let's make the replacements now. Keep the 1/2 out in front. Change the square root of w in the numerator to a u squared. Change the w minus 1 down here to a u squared minus 1. Change the dw to a 2u du. Oops, there's a mistake here. This should be a u to the first power, not u squared. I ultimately do get a u squared because of the other u here. The 2's cancel, leaving me with the integral of u squared over u squared minus 1. I do need to change limits of integration. When w is 2, u is square root of 2, and when w is 10, u is square root of 10, which are not nice numbers. But it is correct. And I could finish this by hand. but I'm not. Because this is a rational function, initially the numerator has the same degree as the denominator, so I would want to use long division, polynomial long division. Once I use that and get a quotient of remainder, I'd also want to use partial fractions. Factoring u squared minus 1 is u minus 1 times u plus 1. I don't want to do that because it would take too long, but I wanted to show you that it is doable. And we can check with Mathematica that it does give the same answer. Though to confirm that it gives the same answer, it's probably best to not do it symbolically, but numerically with n integrate. I tried it symbolically in the last class, and it was doing some funny things with imaginary numbers. So what's the original integral? The original integral is this thing right there. Let me plug in that function, square root of 1 plus 1 over 1 plus x quantity squared. X goes from 0 to 2. You get approximately 2.30, like I said, for the arc length. The line segment was about 2.28. The curve has length slightly bigger, 2.30. They're pretty close together. Let's check that these other integrals integrate the same thing. We'll try this one next, right here. And integrate. It's a capital N and a capital I. 1/2 times the square root of w over w minus 1. W goes from 2 to 10. Yep, same thing. And then the last one right here, and integrate. Yeah, again, the letter you use doesn't matter as long as you're consistent. U squared over u squared minus 1. U goes from square root of 2 to square root of 10. Same thing. Amazing. Okay. So it's working. Emphasizing a conceptual point for the exam that when you do substitution for definite integrals, you got to change the limits of integration.